Hello, class. Last week on Thursday, we left off talking about nuclear radiation on this slide, and we said that radioactive decay occurs when an unstable atom loses energy and it emits radiation. It's spontaneous and requires no energy to take place, and typically both radiation and particles come out of the nucleus. So we talk about four types of radiation: alpha radiation, beta radiation, positron emission, and gamma radiation. And each of the next few slides will go through each of these types of radiation. So this chart is broken down into types of radiation that we just mentioned, the symbol that we use, and the charge. So the first, the alpha particle, we use either the symbol for helium because it's equivalent to a helium nucleus, and you'll notice that there is a charge of 2 and a mass of 4, and then we talk about also using the symbol for an alpha particle. Remember that silly video that we watched with people pretending to be alpha particles for the gold foil experiment with Rutherford? And again, the alpha particle has a charge of 2 and a mass of 4. So again, charge is 2. The second particle we talk about is a beta particle, and again, we use a lot of Greek letters at this point. Notice the charge is -1 and the mass is 0. Again, last column, charge -1. And then we have a positron, and again, charge here, positron, positive, +1, mass is 0. Again, charge is 1. And a gamma particle that has neither charge nor mass. So when we're talking about alpha radiation or alpha particles, as I said, it's a particle that's equivalent to that of a helium nucleus. So it has 2 protons and 2 neutrons, and you'll see you'll either use the helium symbol or the alpha particle symbol using the Greek letter. So an example of a reaction showing this type of alpha particle emission: what does uranium-238 make if it undergoes an alpha radiation decay? And so here I'm showing you that if we started with uranium-238, and for these you have to look on your periodic table to get your atomic number, and if it emits an alpha particle, so here's the alpha particle, then what happens is you get thorium. And again, thorium-234. So it will decay, lose the alpha particle, and it will become thorium-234. Now, it's good to note here that the law of conservation of mass still applies. So our subscript on one side of the arrow to the left of the arrow was 92. And if we add up the 2 subscripts to the right of the arrow, they equal 92. If we go back over here to the superscript here, which is corresponding to the mass, we have 238 for uranium, and if we come over and we add the 2 masses on the right of the arrow, 4 plus 234 equals 238. So when we're doing these problems, you just have to remember that you're going to have to make sure that the numbers on the subscripts and superscripts on both sides of the arrow are the same. So here's a beta particle example. We're starting with a neutron, and we see that it's decaying, and we're getting a proton and a beta particle. Again, adding up the subscripts to the right of the arrow, 1 minus 1 is 0, and to the left, 0. And then again with our superscripts or masses, 1 to the left of the arrow and 1 to the right of the arrow. Here, using carbon-14, showing a beta particle example, a beta particle emission. So you're starting here with your carbon, and it's 6 for the atomic number or the subscript. And if we go to the right of the arrow, 7 minus 1 is 6. Notice here that the atomic number actually went up by 1 because the beta particle is, again, -1. And then our mass, 14 on this side, and 14 plus 0 is 14. So again, the law of conservation of mass is still being adhered to. Then we have an example of a positron emission. So now we're starting with a proton, again 1, 1, and we're getting a neutron and our positron emission. And so again, 1 plus 0 on the right of the arrow equals 1 on the left of the arrow, and 0 plus 1, mass of 1, so our superscripts also add up. Here an example would be with potassium. Again, you'll see 19 is our subscript, our superscript is 38, and if we go to the right of the arrow, we're going to end up with argon. 18 plus 1 is 19, and 38 plus 0 is 38. So here what you would do is you would show the positron particle coming off, and then once you figure out what you have to have as far as subscripts and superscripts, then you go to your handy-dandy periodic table to determine that we're talking about argon. The last example is electron capture, and here that you'll see that what we're doing is we're starting off with an electron and a proton, and we're ending up with a neutron. So -1 plus 1 is 0, that matches. 0 plus 1 is 1, so our superscripts also match. So here we're showing, in this case, silver, and silver is capturing an electron in the nucleus. So 47 minus 1 is 46, so we would write 46. 106 plus 0 is 106. So then if you look on your periodic table, 46 is going to correspond to palladium. So now at this point we're ready to start doing a worksheet, and I'm going to make a second screencast video to walk you through beginning to do the nuclear decay worksheet that's in our Chapter 1 packets.